So hopefully, naming ionic compounds, at least simple binary ones, is going to be a review for you. Okay, you should have learned how to do this during Science 9. But, you know, who knows with the pandemic and whatever else happened, whether that was something that you guys got to or not. Hopefully it is, because it's pretty important. Okay, so we're going to look at naming ionic compounds, naming molecular compounds. Okay, again, hopefully that's review, and then we're going to add on a few exceptions that you would not have learned in Science 9. Okay, that are important for some of the things we do in Science 10 and Chem 20 and Chem 30. All right. So, key points for today. First thing we have to be able to do if we're going to write the name for an ionic or a molecular compound is be able to recognize a compound as being ionic or molecular. Okay, be able to look at it and go, that's an ionic compound, that's a molecular compound. Anybody remember how to tell the difference? Yes. An ionic compound is a metal and a nonmetal, and a molecular compound is two nonmetals. All right, so this, ionic or molecular? It's ionic, okay? Magnesium is a metal, chlorine is a nonmetal, whereas this would be molecular, okay? Phosphorus and oxygen are both nonmetals. And I will get you periodic tables today, okay, so that you have them to work from. All right, and then obviously be able to write formulae and proper names for chemical compounds, right? So we're going to look at the rules, okay, for each one. We're also going to look at the structure for both ionic and molecular compounds and why that gives them certain properties, because later on this week we'll be looking at designing our first lab, and next week performing it, and that'll be on the properties of ionic and molecular compounds. All right, so ionic compounds occur when a metal, from the left side of the staircase, okay, so on a periodic table, you've got this jagged dividing line, okay, that splits it into two parts, not halves, obviously, because there are way more metallic things than there are non-metallic things, okay, so that the staircase runs down, okay, beside like boron, silicon, arsenic, tellurium, and astatine, okay, runs down there. Everything over on that side then would be, on the right, would be a nonmetal, on the left would be a metal, okay. So they react and they form a new molecule, okay. In those molecules, what happens when an ionic compound forms is electrons are traded, okay. Some atoms want to give away electrons. Some atoms want to take them, right? Typically, metals want to give away electrons. Typically, nonmetals want to take them. The reason for that is their structure. This goes back to what Bohr thought about electrons. This is why we still, to an extent, accept Bohr's kind of planetary model. Okay? He said that in the nucleus are the protons and the neutrons, and everybody agreed on that. So here's the nucleus of the sodium atom. But he said electrons go in these rings that go around, okay? And there's different number of electrons in each ring. In the first ring, there are going to be 2 electrons. Okay? And then the next ring can hold 8, and basically every other ring would hold 8 beyond that. Right? Now, how many electrons does sodium have? 11. Okay, its atomic number is 11, so it has 11 electrons. Okay, so 1, 2, okay, and they would pair up like this. Right? So the first ring is full, the second ring is full. That gets me up to 10, right? There's 11 electrons. That ring that single electron is in can hold 8 electrons, but it only has 1 in it. Elements desire to have a full outer ring or outer shell of electrons. The only way for sodium to have a full outer shell is to either pick up 7 electrons from somewhere or find a place to dump 1. What's easier?
Dump 1.
Finding a place to dump 1. Yeah. Okay. Now, chlorine is the opposite situation. Okay. Chlorine has 17 protons, 17 electrons. Okay. So its ring structure looks like this. Okay. 2 in that first shell. Okay. 8 in that second shell. And then 7 in its outer shell. That outer shell can hold 8. It either has to find a home for 7 or pick up 1. What's easier? Pick up one. These two get along famously because they each have what the other wants. Okay, sodium wants to get rid of an atom, or sorry, an electron, and chlorine desperately needs to pick one up. Right, so they will do exactly that. Okay, sodium will donate this electron to chlorine. Chlorine will happily take it, and they will form an ionic bond. Ionic bonds are incredibly weak. Okay, because once an atom has its outer shell full, it's happy. And don't take this the wrong way or put any sociological context to it, but they don't need the other guy anymore. That sounds horrible, but it's true, okay? They really don't, okay? I got what I wanted, see you later. Okay, and that's kind of how ionic bonds work. They're very, very weak, which is another reason why ionic compounds typically dissolve easily in water, why their solutions conduct electricity, okay? Because they can have these charged particles, right? Once sodium donates that electron, it now has one more proton than it has electrons. So it's no longer neutral, now it has a positive charge. Chlorine has picked up an extra electron and it's now negatively charged. We call those ions. The presence of ions in a solution is what allows it to conduct electricity. So you've probably all been told that like water conducts electricity, right? It's not true. Distilled water does not conduct electricity at all. Okay, distilled water has no ions in it, no charged particles, and as a result, does not conduct electricity. Tap water conducts electricity. Why? It's got ions in it. Calcium, chlorine, okay, stuff like that. Okay, all these dissolved minerals. Okay, very rarely do you ever get naturally occurring water that is completely free of minerals. There are a few places. Okay, if you have an incredibly pure well, okay. Has anyone gone to Grossmoor National Park in Newfoundland? Done the big fjord tour? They have a bunch of, they used to be fjords, now they're just cut off from the ocean. The water is so pure that it actually will not conduct electricity, which they found out the hard way when they were trying to make their toilets in the area. Okay, the toilets are supposed to work so that the water level, okay, in the freshwater area is the tank is supposed to say when it's full, because the sensors use conduction of electricity to tell them water level got to here, water conducts electricity, shut the pump off. Except the water's so pure and has no ions in it that the water just went right over the sensors. The sensors didn't trigger the pump to shut off because the water didn't conduct electricity and it just poured out. Okay, luckily it was the fresh water and not the black. That conducts electricity just fine. Okay, yeah. All right, so they make these charged particles called ions, hence the name ionic compounds. So in ionic compounds, we get these weak bonds that result from the trading of electrons. Okay, all right, everybody okay with that? All right. Okay. So simple binary ionic compounds is probably what you learned to name last year. Okay, the name of a binary ionic compound is the name of the metal first, okay, and the name of the nonmetal second. Okay, so the name of the metal stated in full, name of the nonmetal ends in "ide." Okay, so we change whatever the ending of the nonmetal is to "ide" in an ionic compound. All right, so examples could be magnesium oxide, which would be magnesium and oxygen. Sodium fluoride, which would be sodium and fluorine. Aluminum sulfide, which would be aluminum and sulfur. Okay, everybody with me on that? All right, so if it ends in "ide," sorry, you have to make sure your nonmetal ends in "ide" on all ionic compounds. Okay, don't change the name of the metal at all. Okay, we have to remember to name both ions, and this is probably something that was never mentioned to you before, but it's important. The name of an ionic compound, the name of a molecular compound of any chemical, is not a proper name. It's not like John Doe, okay, or any other name of a person. Okay, it's not a proper name. It is a designation. Therefore, it is not capitalized, unless you're starting a sentence with it. Sodium chloride makes my fries taste better. Okay, then you can start it with a capital. Right? Otherwise, the names of chemicals are not capitalized. Okay, a true ionic compound has no charge. because the positives and negatives are going to balance each other out. Okay, we saw that with sodium. Sodium was going to give up one electron and have a positive 1 charge. Chlorine was going to take that electron and have a negative 1 charge. Those add up to neutral. Yeah, they add up to 0. That happens in every compound, right? If I have magnesium go with oxygen, okay, magnesium will give up 2 electrons. Oxygen will take 2. Okay, still adds up to 0. Everybody okay with that idea? All right. That'll become important when we start doing the drop and swap. How many people have heard that term before? Okay, good. Okay. I'm going to hand out some periodic tables now, and I'm going to want you guys to try first 4 on there. Get these 4 here. So first one, okay, I've got, what is my metal?
Sodium.
Sodium, all right. And what's my non-metal? Chloride. Okay. Sodium chloride, done, easy. Okay. Number 2, very similar to that. K stands for potassium. F stands for fluoride. I never spell it right. It's U first, isn't it? No, it isn't. Yeah, it is. See, it's U first, but I always spell it like floweride. Floweride. Because it never looks right to have the U first. Okay, I'm not going to say spelling counts, but like I just messed one up. But I did go over to the periodic table and look up the proper spelling. Given that you do have a periodic table right in front of you, there's really no excuse for you to not be able to do the same thing, okay, and spell them right. Okay, H and I, so H, hydrogen is a metal or non-metal?
Metal.
It's a metal. Weird, it's a gas. It's okay. Metals don't have to be solid, shiny objects. Metals are anything that wants to give up electrons. Hydrogen's weird though, okay? Think about the structure of hydrogen and what we were just talking about a minute ago, okay? Hydrogen has 1 proton, 1 electron. Okay? 1 proton, 1 electron. It needs to fill its outer shell. It needs to do that by what? That first shell can hold how many? 2. So it needs to gain 1. Or have no outer shell at all. That's its preference. Okay? Its preference is to actually give up that single electron that it has. Hydrogen is the most metallic substance there is. Okay? That's why it's the ingredient in all acids. Acids give up electrons incredibly easily, okay? Because they contain hydrogen, right? And so it's going to give up that electron. On the other side of that, it can also pick up an electron, but its preference is to give it up. Okay? All right, so this is going to be hydrogen iodide. All right, here's our first one that's got a little subscript number on it. Does that change what I do with the naming?
No.
Not for ionic compounds, it doesn't. Okay? We never use prefixes on ionic compounds. The reason for that is there is only one possible way for calcium and bromine to go together and end up with a neutral charge. Okay? And that is for there to be 2 bromines and 1 calcium. Because calcium wants to give up 2 electrons. Bromine can only take 1. So there will have to be 2 bromines for every calcium. There's only one way for them to go together, so I don't need to write prefixes. We do use prefixes on molecular compounds because they share electrons. They don't trade them. So they can end up in any configuration imaginable. Not really, but essentially, okay, they can do that. So we have to put prefixes on and say, on this particular molecule, there's 2 phosphorus and 4 oxygens. But on this one, there's 2 phosphorus and 5 oxygens. It can happen. Okay? There's no way for us to know that, okay, because they don't have to balance their charges. All right, so we are looking here at simply calcium bromide. Okay, so with ionic, don't have to put in any prefixes. Okay. Try those ones. See how we do on those. Yeah, give you a few minutes on those. So, let's have a look at these ones here. Number 5, Al stands for aluminum, and that is how we pronounce it here, even though it's not apparently how the International Union of Physics and Applied Chemistry wishes it to be pronounced, because if you look on any new periodic table, not this one because I like this one, it actually says aluminium, not aluminum. I think that sounds silly, because when I drink pop out of a can, it's an aluminum can, not an aluminium can. And I don't drive an all aluminium truck, it's an aluminum truck. Just sounds strange. Okay? So if you spell it wrong, aluminium, I will mark it, even though it seems wrong. Okay, so this is aluminum, and what does the AT stand for? Astatide. Doesn't matter that there are 3 of them. It's an ionic compound, so there are no prefixes. Aluminum astatide. All right, number 6. We've got CS, which is cesium. And it's with S, which is sulfide. All right, so cesium sulfide, again, we don't need to put a prefix on the cesium. There's only one way for those two things to go together. Sulfide is a -2, cesium is a +1, so there would have to be 2 cesium for every sulfide. Number 7, Na stands for sodium. O stands for oxygen, which is then shortened to oxide, sodium oxide. What does Ba stand for? Barium. What does Se stand for? Yeah, so you can write it 2 different ways. You could write it barium selenide, that's fine, or selenamide. Oh, no. Selenamide. Okay, either one is fine. All right, number 9, we got radium and telluride. The name of an SUV now, for some reason. And number 10, Li stands for lithium, and F stands for fluoride. Okay, is this making sense to everybody?
Yep.
Okay. Okay, let's try those last 4. All right, now, there's a few things that you probably haven't seen with ionic compounds that we're going to look at. Okay, there are some metals that are what we call the transition elements, or the transition metals, or multi-valent metals. Okay, the reason we call them that is because there are different types of these metals, would be, I guess, the best way to explain it. Iron is an example. Some iron atoms will give up 2 electrons when they enter an ionic compound. Some will give up 3. Okay? This is shown on your periodic table by having 2 charges listed up in the top right-hand corner. All right, so if you look at iron, okay, which is 26, you'll see that in the top right-hand corner, under its atomic mass, there's a 3+, a comma, and a 2+. Right? Those are the 2 possible charges for iron. Most commonly, iron gives up 3 electrons. But there are some versions of iron that give up 2 electrons instead of 3. Okay? And there are a lot of transition metals all along there that do that. Okay, you can see there's quite a few, starting with titanium there, 4+, 3+, vanadium's 5+, 4+. Okay, basically all the ones along the middle there give up different numbers of electrons. All right, now you're probably thinking, so big deal. What's the problem with that? Well, here's the problem with that. Are those compounds the same? What are they called? What would I name them? Iron oxide. Is that a problem? Well, let me put it this way. I once had 2 Chase William Andersons in the same class. Confusing? Yes. Okay, very confusing. I'm sure both of their marks were probably a little bit out of whack by the end of the semester. Okay, I should have just called them 1 and 2. Okay, by the end, because they had exactly the same name. Okay, first, middle, and last, and they were not the same person. Right? Definitely not. They were very. You could not imagine 2 different people. Okay, but it's a problem when they have exactly the same name. For this, okay. Let's just say, for example, this is rust, and this is highly poisonous. Okay? So if I'm telling somebody, you know what, if you, like, you know, suck on a rusty nail, it can help your hemoglobin, okay, because it's got iron oxide in it, and then they go and take this stuff thinking that would be better, they'll die, and it'll be my fault. I can't have these 2 things have the same name. They're different compounds. They have different properties. Right? So what we have to do is when we write the name, I mean, obviously when we look at the formula, we know they're different. Nobody would confuse these 2 things if they looked at the formula. But if they looked at the name, I was writing a paragraph and I just said iron oxide, that's a problem. So I need to make the names different as well. So what we do is we put in the name a Roman numeral to indicate which iron was present, the 2+ iron or the 3+ iron. If it's the 3+ iron, we put a Roman numeral 3 in the name. If it's a 2+ iron, we put a Roman numeral 2 in the name. Now, how am I going to be able to tell which one it is? So let's try this one as an example here. Copper can have a 1+ charge or a 2+ charge. Which copper is this? This is the copper with the 1+ charge. Okay, how do I know that? Well, what I do is I look at the nonmetal. There are no nonmetals that have more than 1 possible charge. Everything on the right-hand side of the staircase has 1 charge and 1 charge only. Oxygen is always a -2. Right? There are 2 coppers here. Okay? This whole compound needs to add up to a charge of what?
Neutral.
Neutral. That means I need to get 2 positive charges from this side. Since I have 2 coppers, each copper must have a charge of 1. Okay? So I just kind of work backwards and I figure it out. Now, a few people kind of look at this and they go, well, if I just like reverse the drop and swap, won't that work? Not always. Okay? It won't work always. It'll work about 2/3 of the time. I like to be right more than that. I'm not. I would like to be right more than that. Okay, so when we're naming these things, we have to put in a Roman numeral. So this stuff would be called copper 1 oxide. Okay, we still don't put in any prefixes. We still change the ending of the nonmetal to I. All we do is add in a Roman numeral if the metal we're using has more than 1 possible charge. So, do I need to do it for this stuff? Would I need a Roman numeral for that compound?
No.
No. Lithium only has 1 possible charge, so I would just write lithium oxide. Okay, don't need a Roman numeral there, right? But if it's something like this, would I need a Roman numeral for that? Yeah, lead can be a 2 or a 4. Right, so in this case, I would need to write, which one is it? Lead 2 or lead 4? Lead 4, yeah. Because chlorine's always a -1, and there are 4 chlorines, so that gives me 4 negative charges in total. I need to get 4 positive charges, and I only have 1 lead to get it from, so this is the lead with the 4+ charge, lead 4 chloride. So you know, in case you don't know your Roman numerals, because you might not. the Roman Empire fell because their number system sucked. Okay, but that's 1, 2. It's pretty straightforward until you get to 4. Okay, 3. Then we got IV. That's 4 because it's 1 less than 5, which is V. Right? Now, if you've seen like the Rocky movies, you'll follow because there's lots of them. They go by the Roman numeral system, up to 5, and then they became crazy after that. Okay. All right. 6 would be VI because it's 1 more than 5, and then you'd have 7, which would be II. And you're not going to need to go any higher than that for our purposes, but it's VIII, and then it's IX because X stands for 10, and then it's X for 10, and XI for 11, and if you watch the Super Bowl, they always have the Roman numeral on the Super Bowl, and it's getting pretty nuts. Okay, like it's getting bigger and bigger. All right. So in case you don't have those, in case you don't know your Roman numerals, okay, really you shouldn't need more than 5, okay, but we'll go up to 7 just because there is the odd thing for the 7 charge. Okay. Let's have you guys try the first 4 there. Right? Write out their names, figure out which Roman numeral needs to go in their names. All of these ones need Roman numerals. It's here. So our first one, okay, we've got iron and oxygen. So we'll write out the name, but we'll put in the Roman numeral after. Right? It's still an ionic compound, so we still use the same rules. Okay? This is going to start out as iron oxide, but obviously I have to put a Roman numeral in there. I just need to figure out which Roman numeral it is. So in order to figure that out, what I do is I write the charge that oxygen, the non-metal, normally has. It's -2. How many oxygen atoms are in this compound? 3. Okay. So there's 3 oxygens, and each one has a -2 charge. How many negative charges are there in total? 6. All right, so essentially I take these 2 numbers and I multiply them, and that gives me my total number of negative charges. Since that compound has to end up neutral, that means I need to get 6 positive charges from these 2 iron atoms. So I multiply these 2 together. What do I do with these 2 to get my missing number? I divide. Right? I have 2 irons to get 6 positive charges from. That means each iron must have a charge of +3. So this is iron, Roman numeral 3, oxide. Everybody all right with that? Okay, so for our second one, CO stands for cobalt. S stands for sulfur, so that'll be sulfide. Okay, cobalt can be, what, a 2 or a 3? Okay, so it can be a 2 or a 3. Sulfur is always a -2. Now there's 1 of each here, so what's the charge on cobalt?
2.
+2, yeah. I mean, if there's no little numbers, it's easy. They're the same charge because they cancel each other out. All right, so this is the cobalt with the +2 charge. Okay, number 3, we got manganese, that's Mn, with chlorine. So it's going to be manganese something chloride. All right, every chlorine atom is -1, and there are 4 chlorine atoms. So that gives me a total of 4 negative charges. So I've got to get 4 positive charges from the single manganese atom that I have. So the charge on that atom is 4 plus. So this is manganese IV chloride. And then on number 4, we've got copper, which can be a 1 or a 2, with sulfur. Charge on sulfur is always -2, so the charge on copper is going to be +2, copper 2 sulfide. Making sense? Okay. I mean, it's a little bit of math. It's not hard math. It's dividing. It's easy. All right. I want you guys to try the rest of those. They all need Roman numerals. Okay? That's what we'll finish with today. have a quick look at maybe like 5, 6, and 7 here before the bell goes. Number 5 is the first example where just reversing the drop and swap will not work. Okay, because a lot of people just do that, right? They're like, well, I'll just take the number off the non-metal and that'll be the charge. And it is, like I said, about 2/3 to maybe 3/4 of the time. This is one of the cases where that won't work, right? And here's why. This stuff is gonna be tin telluride, but it's gonna need a Roman numeral because tin can be 2 or a 4, or 3 or a 4. 2 or a 4, right? Okay. Now, tellurium is always a -2, which means there's how many negative charges here? 4. So I've got 4 negative charges in total, which means I need to get 4 positive charges from the single atom of tin that is here. That makes this the tin 4, not tin 2, right? Which is what people get if they reverse the drop and swap, and thus it wouldn't be right. It wouldn't have the charges balanced. Okay, questions on that one? All right, so that's why it's important to do it this way, rather than just reversing the drop and swap. All right, so we've got Hg, which is mercury for number 6, and astatine, so astatide. Now, astatine is a -1 charge, so that means there's 2 negative charges. So this is the mercury with the 2+ charge on it. So mercury 2, and it can also be a 1. Okay, mercury 1, mercury 2. All right, and then number 7, we got PO, which is polonium. And it's with iodine. So iodide. Iodine's a -1 charge. There are 4 iodines for a total of -4. That means this single polonium atom must have a charge of 4. Polonium 4 iodine. All right, tomorrow we will have a look at ionic compounds that contain polyatomic ions, and then we'll move on to naming molecular compounds, do a little practice. Thursday's quiz will have a little bit of atomic theory and naming on it, but I'll post it tomorrow. Question?
Do we have to finish this or
No. We'll go through lots of those. Is that your question too?
well, my last one was just on the last one.
Yeah.
So, is it like the ruthenium or whatever, it has +3, but oxygen is a -2, right?
Did they change that? See, I've got 3 and 4 on here as possible on mine. What does it say on yours?
Oh, it's a 3.
Just +3, okay. Well, I'll have to change that
It
one.
makes sense.
Yeah, no, that makes, yeah. See why you're confused. Yeah, they must have updated the chart.
It's kind of a half of it.
These I got these ones, but these ones I didn't put in here. So I guess I was trying to do this for the computer. So you ended up getting like 2, 1, and 2,
Here.
3. Yeah.
Okay, so for the telluride, right? So I look at the charge on telluride, I multiply it by the number of tellurides. Okay, so that gives me 4 negative charges. That means I have to get 4 positive. So I can basically write the same number here, and then I divide this by the number of tin to get the charge. There's only 1 tin, 4 over 1 is. That's the Roman numeral I use.
Okay, wait. So for the 4 on the